So I'm really going to just provide an update of what we've been doing since the last Multicore 9, where I presented. And I showed this slide there, which describes some of the active supercomputing sites where systems are installed throughout the top 500. And I talked about the Perlmutter at NERSC. At that time, we had an architecture we were introducing as Volta Next. We now have released that architecture, the A100, and I'm going to talk a little about some of the features we have on that. All right, so looking at some of the comparison of features from previous architectures, and I'm going to compare directly with the V100, which we introduced in 2017. The A100 was introduced a few months ago, and you can see some of the features there that are kind of highlighted. Certainly, we're going to see higher peak double precision performance, and also memory bandwidth, which I think is important for this community, where we have an increase of 1.7x, and then larger memory capacity from 32 gigabytes to 40 gigabytes. But you'll also notice some other features, tensor core features, other performance that, if you attended the talk this morning by Dr. Peter Dubin, he refers to as deep learning hardware. Certainly those were features designed into the architecture for artificial intelligence style applications, but we're seeing where this can start to benefit scientific computing as well. Dr. Dubin had presented some of that, and I'll show a little bit about what we're doing there. Now, we also introduced a new network interface, NVLink 3, which is up to 600 gigabytes per second over what we had in NVLink 2 at 300 gigabytes per second. And now we're up to a max power of 400 watts, which is standard for most servers that you have available today. The NVIDIA Selene system was mentioned by Raghu in his talk earlier in this session. It's a system based on the A100. A modular system built up of a number of what we call a DGX A100 nodes. These are standalone systems. We have 256 of these in this single system. We introduced it prior to the June 2020 top 500, and it ranked number 7 in that. The system sits in the headquarters, Santa Clara, where I'm located, and you can see some of the specifications there. We also did some really nice work with Mellanox, who was acquired by NVIDIA, to look at how to connect these in node to node using the HDR200 InfiniBand, and we're able to achieve a really high score that got us to number 7 on the top 500. I'm going to show a little bit of performance of what we've been doing with this system here in a moment, but again, based on the A100. So the NERSC Perlmutter will come later, the end of this year, beginning of next. This system is available today that NVIDIA has assembled in order for that top 500, and we do some work on this internally in both HPC and AI applications. I showed this last year, the number of collaborations we have, and I concentrate on atmospheric models since they tend to be most of the projects we have. Certainly we're working on some global ocean model projects. You heard about some of that with the MOM6. I'll talk a little bit about some other work we're doing with MIT on their ocean model. But it's the number of global models and regional models that we've been working with organizations like the DOE, the MPAS you heard about from Raghu earlier, some work with the FE3 at NOAA. You would have heard from John Michalak this morning on the Neptune model, Peter Dubin again for IFS. Chris Maynard this morning talked on the ELFRIC model. And then we've been doing some work with ICON lately. I'm going to highlight some of that later in the talk. And the Clima model, which is comprised of the NUMA atmospheric core from Naval Postgraduate School and the MIT ocean model. I'll show a little bit of work we've done there. And we've been working with the Vulcan organization, another private climate model that's based on the FE3 DICOR. For regional models, we've worked quite a bit with Cosmo, continue to help develop that, and then the Dwarf model. And I'll show you some results there and update. And if you've attended some of the talks, Isaac tomorrow and Luca will talk about some of the work going on at E3SM. Raghu was in this session talking about MPAS. I mentioned John and Peter Dubin and Chris. They all talked this morning and on those 3 global models. And then Thursday, Will Sawyer would talk about some of the work being done in ICON. I'm going to also give a preview there. And then Lucas Wilcox will be on the panel Friday. He works with the Multicore from the Naval Postgraduate School. Now, the way we've accomplished all these collaborations are to invite organizations to join the hackathons that are in progress. I showed this last year. This is really from 2019, the list of models that attended. These were global events. Some actually occurred, if you look at the Met Office. We had a specific event that we held there looking at different models. We did that twice with the Met Office. You'll see a few DOE activities. The Clima had some concentration of focus on the Clima ocean model. We'll talk a little bit about that. We had a specific event on ICON where we held it at ETH and invited MeteoSwiss, MPI, Meteorology, CSCS, just a number of activities. And it's been able to generate a lot more progress in these models and help us bring these forward to more production-like implementations from their start as usually some kind of a mini app or focus on a computational kernel. It's been a very successful program. Again, this is 2019. There's a whole series of these that occurred in 2020. I just didn't have time to assemble that before my presentation today. And here's an example of what's come out of the ICON work that we've done. And I'm showing here various GPUs, but in particular, some test runs we did on Selene for the A100. And if you notice, first of all, for the A100, we're getting very nice performance, 8.4x over a single node of Broadwell. Now, we're not showing the latest CPUs here because we don't typically have those in our lab. We don't always deploy those as soon as they're available for various budget regions. These are all done on internal systems. But you can see the performance that you typically would observe over Broadwell. And this is a relatively coarse resolution here, 160 kilometers and 191 vertical layers. And we chose this particular configuration because it would fit on the single memory of the GPUs that you see shown here. The smallest would have been the P100 on PISDAINT with, I think, 16 gigabytes of memory. The V100 also 16 gigabytes on a DGX1 system, and then the A100 on Selene at 40 gigabytes. And you also notice that between the V100 and A100, we're nearly achieving the memory bandwidth ratio performance. I showed it earlier as 1.7x, and here we're getting 1.6. And also point out here that this work is early. It doesn't include the land model and the radiation. It did include 180 model time steps. You can see the kind of results we're starting to get working with this model and the collaboration of several scientists. Now, we did some further studies. There's a set of configurations available. You can see they range from 160 kilometers to as high resolution as 5 kilometers. Each of these have the 191 vertical levels. And we did some other work to try and look at larger configurations on systems like Selene and others to see what we could achieve. This work is still very early, so I didn't have time to get a complete story together, but you can see a couple of results on Selene here. It's the 20 kilometer configuration where we ran on a total of 208 GPUs. So you've got 8 GPUs per node, 26 nodes. The CPUs on this, by the way, are x86 Skylake based. And you can see the kind of times we're getting for 180 time steps. Same thing for a larger 5 kilometer global configuration, 128 nodes, 8 GPUs per node, so 1,024 GPUs. We're getting to 20 seconds for 180 time steps. And I'm sorry I don't have comparisons on the CPU side as well, so it's really, it just shows you we can get this to run and get it to probably scale. We don't really have a scaling study yet either, but we're getting good results, getting numerical consistency, and hope to go further with these kinds of studies and provide more details as we go. Now, ICON is very important to our program because MeteoSwiss installed a second generation GPU system for their operational NWP. They've got now 44 total V100 GPUs for the Cosmo that they use for regional NWP. They've gone to a complete ensemble prediction system, very successful program with them. And they're planning to migrate Cosmo regional model to a new ICON limited area model, an ICON regional model here during the installation of this system. So very important that we collaborate with them and make sure we get ICON running well for this development. The only other operational system that's currently using GPUs is the one that Raghu had mentioned, using the weather company IBM, using the GRAF model, which is based on MPAS. There they've installed about 300 of the V100s and are producing their daily forecast with that system. And you got a lot of detail about what's happening with the performance from Raghu. I just wanted to mention how pleased we are with these developments. With MPAS, there's a number of resources you might be interested in. I thought Dr. Loft gave a very nice presentation at the NVIDIA GTC GPU Technology Conference. I've noted it there. You can go in and hear the recording. There were several articles and case studies developed by IBM and the weather company. And then at AMS in January this year in Boston, there was a number of talks I thought gave a lot of good detail about how these systems are implemented and the details of the performance that you would find for the operational side of this. And for IFS, I've assembled a similar list. I think if you saw Peter Dubin's talk, you've heard about a lot of this, but we're very excited about some of the work that's been happening on Summit. So I wanted to outline that, or just at least highlight a few things there. This came through a DOE Insight 2020 award that they received, where they've got some 500,000 node hours on Summit. Now, all of these require that you utilize GPUs. If you're familiar with the DOE Insight for the Titan system, there was no requirements that the GPUs be utilized to be awarded one of those, but for Summit, it was different where GPUs must be utilized. So we're starting to look at some studies of the IFS, and their interest was to compare some of the spectral versus finite volume implementations. I'm certain Dr. Dubin gave a lot of detail on that, but it started with the ESCAPE project that we joined in 2017 as one of the 11 members. And this story has been told many times. I won't go into details, but there was a spherical harmonic dwarf and then an advection dwarf. We've got some really nice performance on these. This is based on their spectral model. This is what got implemented into the work that they're doing on Summit. So they've shown some scaling to up to 11,500 plus GPUs on Summit today. This shows a study, there's a reference below, where they're looking at the performance on Power 9 at the large scale. The number of MPI tasks would be the number of GPUs. So not number of nodes, but for the IBM, that would be 2 CPUs per node. You've got 6 GPUs per node. You can do the arithmetic there to see how we're doing on the CPU versus GPU. But what you do notice about the NVIDIA result, and this is kind of reversed where normally the colors would be green for the GPU, blue for the CPU. It's been reversed in this chart ECMWF produced. But you can see that based on ideal scaling curve, the Summit GPU performance is doing really well. And you've probably heard this study this morning about the use of deep learning hardware, as I mentioned. And this is some research where ECMWF is partnering with organizations like Oxford University, Professor Tim Palmer. And this comes from work that was started out of that lab and was presented at the PASC 2019, where it won Best Paper Award from Chris Hatfield. Now, Chris was a postdoc, I believe, at Oxford and has since joined ECMWF, and they're continuing this research. And it's essentially about putting the Legendre transformations, which are largely gem-based, matrix from his multiplies, and finding out what kind of performance can be achieved using the deep learning hardware, some of the features on the new A100 that I mentioned, and how that might contribute to the overall performance in a large global model. And I mentioned the Clima development. It's a very interesting model where they're applying a global model based on the NUMA from Frank Gerardo. And I mentioned Lucas Wilcox as part of this. He'll be talking at the panel on Friday. But they're combining elements of HPC and machine learning, the HPC side having a global model, such as the atmospheric core of NUMA, or an ocean model based on MIT GCM, and combining data observations and having feedback there through AI mechanisms, and then applying these sub-grid scale models through superparameterization. There's references that you can go and read about some of the details of the model and get into that. But we did some work at one of the hackathons I showed at MIT, where we took the LES ocean models at the time called Oceananigans. I'm not sure what the final development, or sorry, name of the model would have been. But it's a model written in Julia, again, based on some concepts from MIT GCM. People like Chris Hill and John Marshall are associated with this. And we show what performance we're able to get by placing a single LES ocean model on a per GPU basis, and then using these for the subgrid scale model that we're using in this configuration with the global model and the data observations. Really nice work. There's a presentation you can reference at the Oxford conference in September 2009 last year that can give you more detail about what was achieved through this collaboration. And I'm going to move now to regional models. I'll start with, sorry, I'm only going to talk about WRF, not the Cosmo. But WRF has made a lot of progress. I tend to highlight this each year. And as a summary, we're now up to 25 physics options. This is a model. It's still based on the development of ARW release 381, so Advanced Research WRF DICOR. 25 physics features, which you see listed there. And it's a collaboration between NVIDIA and an organization called TempoQuest, which is commercial. Although we have developed together this WRFg, it's called, a community model. You can download and run this without any cost, but it would only be downloaded in the form of an executable that you could test. But it's ready to test if you're interested in what you might be able to achieve and results. It does have some CUDA, so it would run only on NVIDIA GPUs at the moment, but it will also run on CPUs. You can test that mode and find out what kind of performance is possible. So we did some benchmarks that I'll show you here on a system we call Prometheus, which is based on the V100. We did some work on A100, I'll show that as well, but most of what you're going to see is based on this Prometheus system, 36 DGX V100 nodes, which would be V100s with Broadwell CPUs, each GPU with 16 gigabytes of memory. The first case would be one from an organization in Italy called CINECA. It was an actual case that was developed for wind farm simulations. And you can see that we're running a single domain here of 42 million points, 1.5 kilometer grid spacing. And we're able to achieve here a 13x speed up for the full node, which would be 6.5 if you're looking at socket to socket. We're going to continue to scale this later on their system called Marconi 100, which is a sort of Summit-like architecture, but it has 2 + 4 V100 GPUs, so IBM-based P9 CPUs along with 4 V100 GPUs. And this work was to prepare for that as we move forward. This gives you just a view of that from projected results socket to socket versus actual run results that we achieved the 13x speed up over the using 4 GPUs against 2 CPUs. IITM is another organization working with. They're the India Institute of Tropical Meteorology. They've got a prediction system based on Dwarf. This is their operational NWP. Here we looked at a single domain again, nearly the same size that you saw earlier, but here we've got 9-kilometer grid spacing, and the list of physics that you see there. Ran this on the same Prometheus system, and you can see we were able to achieve about a 10.5x speed up for 4 GPUs again versus 2 CPUs. It was a very interesting study because they were actually using the new CONUS physics suite in Dwarf. And if you notice, here we use for surface layer revised MM5 and for planetary boundary layer YSU, we had made those modifications in order to run this fully on the GPU. But then later, TempoQuest actually developed the full CONUS physics suite on the GPU. The 2 missing physics options were the MYJ PBL and the ETA similarity scheme for surface layer. And you can see once those are implemented, we're able to achieve the same level of performance in the 10.5x speed up that we saw earlier. So now we're actually getting full speed up of what's expected for their actual operational case, and doing that with the actual physics they want, along with numerical consistency. So a very successful story. Now, this study I'm showing you was just a single node, similar to the CINECA case. We're starting there, but we've started to do some scalability studies, and I hope to share more with that in the future as we develop those. And the final case I'm going to show is one from NCAR, looking at a larger number of grid points, in this case 113 million. What I showed you previous were all under 50 million. This is a 3-kilometer grid spacing, and you can see the details of the physics that were used. And the same thing here, we had to modify this. This was using CONUS physics suite, but we had to modify this to get it to run. It predates what I showed you earlier, so we haven't gone back to run the physics, the CONUS physics suite. But again, we ran the revised MM5 for surface layer. Planetary boundary layer was YSU. Everything else matches what's in the CONUS physics suite. And you can see here, we're seeing really nice results on Selene, in this case for the A100. The V100 again was that Prometheus system I showed earlier on the chart, but the A100 comes from Selene, where you've got A100s and Skylake CPUs, and there we're seeing about 14x for the 4 GPUs versus 2 CPUs. Same kind of metric that I showed on the earlier ones.
I'm sorry, Stan, can you, this is a time check, you're a little bit over.
Sorry, Rich, I believe that's my last slide.
I hope so. Because you're
thanks, Rich. That's
4 minutes over, man.
Oh, sorry about that.
So
well,
just wrap her up. Yep, go.
Sorry about that. I'm ready for questions, thanks.